Okay, so this is the second part of the Introduction to Organic Chemistry, and we're going to be focusing on isomerism in this topic. So perhaps what we should start with is just making it clear initially what we're going to mean by an isomer, because we're going to be talking about different types of isomerism shortly. So isomers are molecules that have the same molecular formula but a different arrangement of atoms in space. So if we can remember in the first video what we meant by molecular formula, that told us how many of each element or atom there were. So we could have a molecular formula of, say, C3H6O. So we know from that formula there are 3 carbons, 6 hydrogens and 1 oxygen in the molecule. But actually what that formula doesn't tell us is how those 3 carbon atoms, 6 hydrogen atoms and the 1 oxygen atom are joined together. And in fact there were 2 possibilities, if you remember, and when we looked at that particular molecular formula, we could have had an aldehyde. So we had this structural formula, so do you remember that's a structural formula? Or we could have had a ketone, so we could have had something. Have had this, which is a different structural formula. Okay, so we're going to look at isomerism in greater detail, and there are different forms of isomerism too. So one way of showing the different forms is in the form, well, as I've done here, which is like a family tree. So everything in this family tree is an example of an isomer, right? So we've got isomers at the top there. We can then get 2 sort of classes, types of class, or classes of isomers, I guess, is one way of putting it. We could have a structural, we can have structural isomers, or we can have stereoisomers. And within the structural isomers, there are 3 types of structural isomers. There's the functional group isomer, a position isomer, and a chain isomer. And then in the stereoisomers, there are 2 types. There's geometric and optical. So we're going to look at all of those actually, except the optical stereoisomers during the course of this video. So we're going to look first at structural isomerism. Okay, so in structural isomerism, we have the same molecular formula. So this is going to be true actually of all isomers. They are all going to have the same molecular formula. And in structural isomerism, what we're then focusing on is the fact that they have different structural formulae. So we saw an example of that right on the first slide where I did the C3H6O, and I had 2 structural isomers. I had CH3, CH2, CHO for the aldehyde, and I had CH3CO, CH3 for the ketone, and they were different structural formulae. So those atoms were joined together in different ways. The same atoms were joined together in different ways. So as we saw in the family tree, we can break structural isomerism down into 3 types. So one of them is chain, which we're going to look at first, then position, and then functional group. So chain isomerism comes about because of branching, in essence. So actually what I probably should do here is just add the hydrogens. Okay, so there they are. So they both have the same molecular formula. They both have the molecular formula C4H10, and yet we can see that the atoms are arranged. So structure A is butane, and we can see that we can have 4 consecutive carbons in our chain. Structure B is methyl propane, and the maximum we can do is 3. So they have the same molecular formula, but due to branching, the atoms are joined together differently. And so we have, in this example, structural isomerism, and specifically chain isomerism. So here we have a question asking us how many different isomers, and it's going to be chain isomers, of C5H12 there are. Now, I'm actually going to use this as an opportunity also to practice some skeletal formulae, or to go over skeletal formulae. Whilst in the final exams, you are being asked to draw skeletal formulae, probably out of 300 marks, it's not going to amount to more than an absolute maximum of 3 marks. I think as a method of working, or a way of working, and a way in particular of working out isomers, I think it provides a really useful tool to working out different isomers. It's much quicker than drawing out all of the atoms and so on. And it's also, I think, easier to sort of have a system. So when you're looking at chain isomerism, one thing that you should always start with if you're trying to work out how many isomers there are is the simplest version that you can give, which is the straight chain version. So 1, 2, 3, 4, 5. So just to remind ourselves, it's about skeletal formulae. Each sort of point on a line is a carbon. So we've got 1, 2, 3, 4, 5. Okay, so we've got our 5 carbons. And we also know that carbon always has to have 4 bonds. So we look at how many lines are from each one of those carbons, and we make it up to 4 by thinking about how many hydrogens there are, in fact, on that molecule. So 1, 2, 3. Okay, so that's now got then 1, 2, 1, 2, 1, 2, 1, 2, 3. Okay, so those would be hydrogens. Okay, so we have our C5H12. Okay, so I'm just going to rub those out now, because that's not the skeletal formula anymore. I don't want to show the skeletal formula, but I just wanted to remind you of what skeletal formula was representing. Actually, I had to end up redrawing it. Anyway, that's our first one. So we can't do any other different straight chains based on 5 carbons. So the next thing to do would be to draw a straight chain with 1 fewer carbons. So 1, 2, 3, 4. And then we've got a carbon left over, and it's all about branching, so we're going to put it on a branch there. Okay. Something to be just wary of is if I'd drawn it like this and put the branch here, they are in fact the same thing. Okay, so we still have only drawn 2 different isomers so far of C5H12. If you don't believe me, if we were to name this compound, it would be, well, it would obviously be butane, and then it would be 2-methyl. And if we were to name this compound, it would also be 2-methyl-butane. Okay, so 2-methyl-butane is to both of them. So there are no other possibilities in terms of branching off our 4 carbon chain. So now I'm going to take it down to 3. Okay, so 1, 2, 3 carbons there. I can't put the branch at the ends because that will just make it a 4 or a 5 carbon chain. So the branches have to go at the second carbon, and both of the branches will have to go there. Okay. And so that would be, well, it's obviously propane, and there's 2 methyl substituent groups on the second carbon, so it would be 2, 2, well, in fact, I don't have to put the numbers because they can only be in one place, sorry. So it would be dimethyl propane. And that's it, that's all I can do. So the answer to our question here is 3. Okay, there were 3 different isomers of C5H12 that we could draw. So position isomerism is to do about the position of the functional group. So in our example here, we've got a 4 carbon chain alcohol. We have 2 versions, one in which the OH group is on the first carbon and one in which the OH group is on the second. So these are position isomers of each other. So here we're being asked to draw and name all the position isomers of pentanol. So the fact that it tells us it's pentan means that in every example, or every one that we're going to draw, there are going to be 5 consecutive carbons. So in every example, I'm going to be drawing, and I'm going to use my skeletal formula again, my 5 carbons. So then the question is, where can the OH group go? Well, it could go on the first carbon. It could go on the second. And it could also go on the third. Okay. So we would have our different isomers are pentan 1-ol, pentan 2-ol, and pentan 3-ol. And just to sort of confirm the numbers, 1, 2, 3, 4, 5. Okay. Just to say, if you've got a group, just to make it clear, I know you might be querying the fact that we've got this line here, but that's just showing the bond to the OH group. So in terms of carbons, there's still only these points of the zigzag, I guess. So those are the points that are the carbons. And the final type of structural isomerism is functional group isomerism. This often throws students, or can throw students in exams, but actually, particularly by the time you get to the final exams, there really aren't that many. Well, it comes in pairs. Basically, functional group isomers come in pairs, as we'll see in a second, and as we can also start to see here. And if you are sure about one of the pairs, then you can be reasonably confident about the other. So again, this is something actually that we looked at the beginning. So when we did the molecular formula C3H6O, and we said that we could give different structural formulae, we can now see that in terms of structural isomerism, they were examples of functional group isomerism. So we have an aldehyde, okay, and we have a ketone. And even though they both have the carbonyl group, they're going to be treated as different because they're different homologous series. So even though they're the same functional group, they do have different consequences in terms of the reactions they can perform. And then two other pairs, carboxylic acid, so something like propanoic acid, and its functional group isomer is going to be an ester. And there might be actually more than one type of ester it could be a functional group of. So this could have been ethyl methanoate, for example. And then the one that actually proves to be much more common in exams, alkenes and cycloalkanes. And if you remember right back near the beginning of the first video, I mentioned about how general formulae weren't always terribly helpful. If you look at what the general formula for, if you remember what a general formula of an alkene is, it is CnH2n. Well, we now know that that could also apply to a cycloalkane. So we've got to be a little bit wary now of relying on general formulae. Okay. So this is a classic type of exam question to do with this particular area. So we've got two molecules, A and B, and they have the formula C5H10. So they have the same molecular formula. We're then told that A decolorizes bromine water. So what does that tell us? Well, that tells us that it must have a carbon-carbon double bond. That was the test for an alkene. You did that at GCSE. And it tells us that B does not decolorize bromine water. So what can we infer from that is that it does not contain a carbon-carbon double bond, right? And yet, if we were relying on molecular formulae and general formulae, we'd be looking at something we always assumed was an alkene. So for A, we just have to draw any alkene with the molecular formula C5H10. So I've just kept it simple, and I've just drawn pent-1-ene, okay? Just remember that it's 1-ene because the carbon-carbon double bond starts on the first carbon. Okay, so I now have to consider what molecule B is, or could be. It's not an alkene, and yet it has the same molecular formula as an alkene, and this is where you have to make that connection. Think of those pairs when it comes to functional group isomerism. We know we've got the functional group C, double bond C in one, and we know we don't have that in the other. So we are looking at a cycloalkane. So there are a few possibilities, but perhaps the most straightforward and obvious would be cyclopentane, but it could have also have been methyl cyclobutane. Okay, any queries about that though, please just let me know. So just to sort of consolidate that functional group isomerism, pairs of functional group isomers, ones that go together, are obviously alkenes and cycloalkanes, which is what we had in the previous example question. Aldehydes and ketones, although that's really not going to appear till probably the end of year 12. And then carboxylic acids and esters, which are really not going to appear until the beginning of year 13 when we do those topics. Okay, so this question is asking us to draw the 4 structural isomers of C3H6Cl2. The first thing to say is that if I have only 3 carbons, there is no possibility of chain isomerism, because there's no possibility of branching something with only 3 carbons. So every one of my isomers, if I'm going to use skeletal formulae, which I'm going to because it makes life a lot easier and quicker, and I think it's good for you to sort of consolidate your understanding of skeletal formulae, every single one of them is going to be like this. Okay, so that's my 3 carbon chain. Okay, 1, 2, 3 carbons. So to determine the 4 different structural isomers, what I'm going to do is, because you want to be systematic, I'm going to put the 2 chlorines, both of them on the same carbon at one end. Okay, so there's the first and there's the second. And then I'm going to leave one of them fixed, or I'm going to leave one of them at the end. Then I'm going to move the other one to the second carbon. And then I'm going to move it, still leaving the first fixed, sorry for these not very straight lines, to the final carbon. So, being systematic, I put them both at one end, and then I kept one of them in a fixed position and moved the second chlorine along the chain. So there are 3 possible variations there. So I've exhausted looking at a chlorine I've exhausted looking at the chlorines at the end of a chain, but I haven't looked at them if they're in the middle. So I'm going to put them both on the second carbon, and those are my 4 structural isomers. So they are position isomers, because the functional group is the carbon halogen or the carbon chlorine. That makes them haloalkanes. And they are in different positions, which is why they're position isomers. They're not functional group isomers because we haven't changed the functional group, and they are not chain isomers because they are a 3-length chain in every example. Okay, so there are our 4. Okay, so now we're moving on to stereoisomerism. So if you remember the family tree right at the beginning, from isomers it branched into structural isomers and stereoisomers, and the structural isomers part branched into chain, position and functional group. So we've looked at those. Now we're looking at the other first branch, which is stereoisomerism. So in this example, so structural isomerism was the same molecular formula but different structural formula. Here we have the same structural formula, but we have a different spatial arrangement of atoms. So the way they are arranged in space is different, even though they have the same structural formula. So you can't tell the stereoisomerism just by glancing at a structural formula. It gets divided into 2 areas. It's divided into geometric isomerism, and that's what we're going to be focusing on now. And the other thing it focuses on is optical isomerism, but we won't do that until towards the end of year 12. So we're just focusing on geometric isomerism in this particular video. So the first thing to say is that geometric isomerism can arise in alkenes. It doesn't mean it always arises in alkenes, but if it does arise, it's going to be in alkenes. And the reason for this, and you're just going to have to take this as read for the moment, you'll get a better understanding of it when you come to do alkenes specifically. But the carbon-carbon double bond, it cannot rotate. Can't do that, right? It's restricted rotation. That's how we describe it. It possesses a restricted rotation. So everything that follows is because you have this restricted rotation around a carbon-carbon double bond. Okay, so let's just explore that in a little bit more detail. So these images are taken from a really, really good website called chemguide.co.uk, so I definitely recommend that. All right, so in the molecules at the top, we just have a single bond between the 2 carbons. So the 2 carbons are the black circles, so they represent carbon, and there is a single bond between them. In fact, I'll tell you what, what I'll do next to them is the displayed formula of these. So they are exactly the same molecule, okay? So this molecule is able to rotate, or we could twist it around that single carbon-carbon bond. We could just literally twist or rotate the molecule so that we had the chlorines on opposite sides or the same side. However, we can't do that when there's a carbon-carbon double bond. So we have a very clear different spatial arrangement. We've got the chlorines on sort of, I guess you could call them opposite sides or across from each other. Maybe across from each other is better, actually, thinking about where we're going next. Or they are on the same side, okay? But you can't twist one into the other like you can with the haloalkane at the top. So the simplest form of geometric isomerism is cis-trans isomerism. So if the groups are on the same side, then we call that cis isomerism, and if they're on across from each other, then we call that trans. So if we were naming these two isomers here, they would be called cis 1,2-dichloroethane and trans 1,2-dichloroethane. So we'd be able to differentiate the two molecules through the use of the cis and the trans at the start of their name. So we'll just have a go at identifying whether the following molecules exhibit cis-trans isomerism or not. The way to approach this is to start with your carbon-carbon double bond, and then and you're going to be drawing it like this, okay? And then if you do them at those sort of 45-degree angles, it'll make life a lot easier. We know it's butene, so we know that the carbon double bond is on the second carbon, so we must have a CH3 here, and we know it's got to be 4 because it's but, so we'll end up with a CH3 here, and this must be an H, and this must be an H. It doesn't matter which side I've drawn them, we're just trying to identify whether we could have cis and trans. What I've drawn here is clearly the trans, the across version. So yes, we can have cis or trans in this particular example. So if we look at the next one, we've got to start again with our carbon-carbon double bond. It's pent-2ene. We're told that the second carbon is the start of the double bond, so we're going to have a CH3 there. I should have drawn those like that, sorry. Third carbon's got a methyl, so 1, 2, 3, so we'll put the methyl there. And it's pent, so 1, 2, 3, so this must be CH2, CH3, and then that must be an H. Do we have different groups? Yes. And actually, funnily enough, I've drawn the trans version again. Dichloropropene. Okay, so we can only go. Okay, so it's propene, so we don't have a number because it has to be the first carbon. So let's just put the CH3 there. We're told that we've got a chlorine on the first, a chlorine on the second, and we must have an H there. That's a bit tricky. So I think we could have the chlorines on across or on the same side. So that does suggest cis-trans. And then looking at the last one, I don't think it is possible to say that's cis or trans. We've got there's no way we could swap the sides where we could differentiate between the two, or differentiate between versions. So I think there is only one version of the one at the bottom. But if you want to query that with me, by all means get in touch. Now actually, when it comes to the final exams, there isn't actually very much about cis and trans. In fact, the only time that really becomes meaningful is actually in the very final topic that you'll do in year 13, which is on transition metals. And one of the reasons for this is because cis-trans isomerism as a description actually falls apart quite quickly. So if we look at this example here, which is again from Chem Guide, I've taken the images from a Chem Guide, it's not clear that we can see they're different. We can see that they are geometric isomers. We can see that they have the same structural formulae but have a different spatial arrangement of the atoms. But it's not easy for us to describe one as cis and one as trans. So we're going to need a more advanced system for sort of determining or identifying these two geometric isomers of each other. So we come to a system, or we come to something called EZ isomerism. And this is based on this Cahn Ingold Prelog sequence set of rules. Now, you just need to know that name because in an exam question, sometimes they can say, use the UPAC Cahn Ingold Prelog rules to determine, etc., etc. So you need to recognize that Cahn Ingold Prelog is basically flashing to you that you're going to be doing EZ isomerism here. So I'm going to talk through the rules, or the way of considering rules. They won't mean a great deal until we look at an example, but that's what we're going to do first, okay? So remember, we're talking about alkenes anyway when we're talking about this type of it, when we talk about geometric isomerism. So we're going to be looking at the atoms that are attached directly to the carbons in the carbon-carbon double bond. We're going to look at, say, which atoms are attached to the carbon on the left, and then we're going to look at the atoms attached to the carbon on the right. So when we look at one of those, look at the atoms attached to one of those carbons, so let's say the carbon on the left of this carbon-carbon double bond, we are going to assign priority, okay? And to determine which of those atoms that's attached to the carbon in the carbon double bond has the higher priority, we're going to look at which of them has the higher atomic number. We're going to do that for both sides of the double bond. So the left-hand carbon, we're going to look at the atoms attached to it and assign a higher priority to one of those atoms. And then we're going to look at the right-hand side and do the same. And if the groups with higher priority are on opposite sides, so like the trans, like the across, then we're going to give it the label E. And if the groups of high priority are on the same side, and that is a way of trying to remember which is E and which is Z, so if they are on the same side, so that's a bit like cis, so they're on the same side, then we assign the label Z. Now, it can get a little bit more complicated because sometimes the atoms attached directly to the carbon of the carbon double bonds have the same atomic number, and so they at first glance have the same priority. So then what we do is we look beyond those first atoms and see what the subsequent atoms, what their atomic number is, and we try and distinguish them between them. So that probably doesn't make a lot of sense at the moment, but we're going to look at some examples and then hopefully it will. Okay, so we're going to look at these two molecules and we're going to determine whether they are E or Z isomers. So I'm going to just draw a dotted line down the middle. Okay, so what I'm going to do is I'm going to focus on the left-hand carbon first, and then I'm going to focus on the right-hand carbon. Right, okay, so on the left-hand carbon I've got fluorine, and fluorine has an atomic number of 9. Okay, and if when I look at the other atom that's attached to that left-hand carbon in the carbon double bond, it's another carbon that has an atomic number of 6. So in terms of which one has the higher priority, 9 trumps 6, so the fluorine has the higher priority on the left-hand carbon. So if we look at the right-hand carbon, the atomic number of bromine is 35, okay, and the atomic number of carbon is 6. So if we consider which of those has the high priority, clearly 35 has the higher priority than 6. So let's now name this molecule. So let's focus on the main part of the name first. So we have a 4-carbon chain, so it's bute. The double bond is on the second carbon, so it's bute-2-ene. So bromo comes before fluoro alphabetically, so we're going to be counting it also from the right-hand side. So it's going to be 2 bromo, 3 fluoro. Okay, so we've got 2 bromo, 3 fluoro, bute-2-ene, and we've established that the high priorities are on the same side, and so it is a Z, 2 bromo, 3 fluoro, bute-2-ene. Okay, so now we're going to look at the bottom one. So again, I'm just going to do that dashed line, just helps, I think. All right, so if we look at the left-hand carbon, we look at the atomic numbers of the atoms attached to the left-hand carbon. It's 1 for hydrogen and 6 for carbon. So clearly in terms of priority, higher priority, it's going to be the carbon. Then if we look at the right-hand side, initially it's a carbon on both of them that's attached to that carbon on the right. So that's when we look at the next atom. So the next atom is going to be 6 there because of the second carbon, but it's only going to be 1 at the bottom right here because it's only hydrogen that's then attached. So if in terms of higher priority, it is going to be the one in the top right because we've got a 6 and then a 6 rather than a 6 and then a 1. So here we've got an E geometric isomer because the higher priorities are on opposite sides from each other. So maybe you want to just have a think of how you would name this compound and then pause the video and then I'll give you the name. So it's E3 methyl pent-2-ene. So the carbon double bond is on the second carbon. That takes priority in our numbering. So the methyl group is on the third carbon and our longest chain is a 5-carbon chain, hence pent. Okay, so E3 methyl pent-2-ene and the E because our highest priorities either side of the carbon double bond are on opposite sides from each other. So we're just going to do a quick task. And we're just going to first of all try and see if these two molecules would exhibit isomerism, and if they did, would they be E or would they be Z, or depending on the version I draw anyway. So we've got methyl propene. So the first thing I think to make life a lot easier in all of these examples is to draw the carbon-carbon double bond first and to just draw our 45-degree bonds off them. It's methyl propene, so the propene means we've got 3 carbons, and our methyl can only be in one place. Actually, it can only be on the second carbon because if I put it either on either of the left-hand bonds, it would now be a 4-carbon chain, so that wouldn't work. So, well, I hope you can see straight away, or begin to see straight away, that this cannot show EZ isomerism, and that is because when you look at the groups attached either side, they are identical. So you can't do it. So it's not possible. So no EZ here. Okay. I mean, a rule of thumb is if you've got a carbon-carbon double bond at the end of a chain, so it's on the first carbon, assuming that you only have hydrogens attached to that very first carbon, like we do on the left here, then you cannot have EZ isomerism because instantly, straight away, you've got 2 groups where there is no higher priority. They're both H's. They both have the same priority. All right, let's have a look at the one underneath. So again, it's propene. So that's our propene part. And it says it's 1 chloro, so on the first carbon. So I'm just going to put it up at the top for the moment. Could have been at the bottom, could have been where I've just put that H, and that's an H. Let's just draw our dotted line, and let's just assign our priority. So the atomic number of fluorine is 17, for hydrogen it's 1. So in terms of our priority, clearly that 17 is greater than 1, so chlorine is high priority. Look at our right-hand side, hydrogen 1, carbon 6. Clearly then our carbon is of higher priority, our methyl group is of higher priority. So we do have different priorities on both sides. In terms of this, we've got them on opposite sides. So the isomer that we've got here is an E geometric isomer. Okay, so there's a lot more practice that you can do if you look on the classroom at the worksheets that I've posted there. So just to summarise, this whole video was about isomers. We saw that we could talk about structural isomers or stereoisomers. In structural isomers, they all had the same molecular formula but different structural formula. In stereoisomers, they have the same structural formula as well as the same molecular formula, so the same molecular formulas are given, but the atoms were arranged differently in space. The structural we could break down into functional group, position, and chain. So a functional group was that they had the same molecular formula but different functional groups. Position isomers had the same molecular formula but the position of the functional group was different. And in chain they had the same molecular formula but we had the possibility of different branching. And then in the stereoisomers, we only looked at geometric. Optical is something that we'll look at in the future. And in geometric isomers, we had the same structural formula, but due to the presence of a carbon-carbon double bond, there was the possibility of a different arrangement of atoms in space. So any queries about isomers, you know where I am, but hopefully most of that made sense. Thanks.